Thank you very much. Thank you very much for inviting me. It's a great honor, a great pleasure to talk at the conference in honor of Sylvia and Roger Wiegand, who are great people. I guess I felt that I knew you quite well in the late 80s, 1990s, but then we haven't seen each other for a few decades. But anyway, happy 150th birthday. And so as it turned out, I'm giving two talks almost back to back. I'll give another one on Sunday. So I decided today to just make a general introduction to the subject and on Sunday to say more recent things about more recent work. And there will be some intersection with what Franz Victor said, but I hope, well, you know, in Russian there is a proverb that repetition is the mother of all learning. but also I think we have complementary approaches, so there'll be some intersection, but the explanations will be different. So let me remind you what Franz Victor already said. So I start with an algebraic variety. Algebraic over a ground field K. We could make it much more general. It could be schemes or analytic spaces, but in this talk, let's stick to varieties. So of course we have a notion of morphisms in the category of algebraic varieties. So a morphism is called birational. A morphism between two varieties is birational. And I'll be talking for now only about irreducible varieties, okay, defined by prime ideals. So it's birational if there exist proper subvarieties such that pi induces an isomorphism outside of these subvarieties. So I'll give at least one example in a minute, or actually I'll give many examples. And as Franz Victor said, this is equivalent to saying that my morphism pi induces an isomorphism of fields of functions on these varieties. This is so because what this says is that these two varieties, x and x prime, share a Zariski open set in common. And any Zariski open set determines the field of fractions. So if they have a Zariski open set that's isomorphic, then the fields of functions must be isomorphic. So, and a resolution of singularities. So a resolution of singularities. So I start out with a singular of singularities of x is a birational proper morphism such that x prime is not singular. Well, most people probably know what proper means, but for those who don't, I'll say if we're working over real numbers or complex numbers, this is just the usual proper in topology. The preimage of a compact set is compact in the classical topology. And it's a little bit harder to define in characteristic P, but it can be defined. Basically, it means that there are no holes in the fibers of the morphism. Okay, and obviously we need this word proper here because if I didn't say proper, the problem would be trivial. You would just take x prime being x minus its singular locus. That would be the resolution of singularities. The usual technique for, or at least most of the proofs of resolution of singularities work by embedding x into an ambient non-singular variety and then doing something, blowing up this non-singular variety and seeing how x transforms. Okay, so let me give some examples, or let me define blowing up for future reference. I'll need this later in this talk and also in my talk on Sunday. So maybe the first, okay, the most obvious, simplest example of resolution of singularities, think of a nodal curve think about this curve. It has one singular point, so it's a point which doesn't look like a piece of Euclidean space if you look under a microscope. And intuitively, geometrically, resolution of singularities here just consists of taking the two branches apart, right? So by the way, this I'll refer to this. Y is referred to usually as center of blowing up. Center of blowing up. And this is referred to as the exceptional set or exceptional divisor because it's often a divisor. Okay. So resolution of singularities consists in removing the singular locus and gluing something else in its place in such a way that the whole becomes non-singular. Of course, we're algebraic geometers, so instead of drawing pictures, we have to do everything algebraically. So let me define. So this singular variety is embedded in a plane. So let me define blowing up the plane at a point. Blowing up the plane at the origin. So what we do is we consider the totality of straight lines which pass through the origin. This set of straight lines is parameterized by P1. So the center of blowing up in this case is going to be the origin of the plane, and the exceptional divisor is going to be the P1 that parameterizes these lines that pass through the origin. Okay, and so I replace the origin by P1, and everything else remains unchanged. So if k is the real numbers, you can think this is just a Möbius bend, right? This is a line which goes around once. And again, since we're algebraic geometers, we must be able to write everything down with equations. So here the coordinate ring is a polynomial ring in two variables. And upstairs, my variety is glued, is no longer affine. It's glued out of two planes. And I think of coordinate rings in this way. I mean, you should think of this notation as a formal, these are just formal variables, but all the transformation laws, it's a convenient notation because all the transformation laws from downstairs to upstairs and also between the two coordinate charts are encoded already in the notation. Okay, so for example, in this coordinate chart, y over x parameterizes the slope of the line. It's the coordinate along the exceptional divisor, and x is just the transversal coordinate. So for example, now I can explain this example much more rigorously, right? Because I started out with this equation. I have to see what it looks like, what the new variety looks like upstairs. So I just have to make the substitution. So I call this, let x prime be x and y prime y over x. So that means that in this coordinate chart, y is x prime, y prime, x is x prime. So I just make the substitution. And so you see now, this polynomial is reducible. My variety has become reducible. This is to be expected. So my curve was here. My singular curve was here. What I'm computing here is the full preimage of my curve upstairs. In particular, it contains the entire exceptional divisor. It contains the preimage of 0. So it contains all the P1. So I expect the new curve to be P1 plus another curve. And this is indeed what happens, right? So the total preimage of my curve is the union of the line, P1, and the parabola. And so to get something birational to the original curve, I must remove the exceptional divisor. That means I must factor out the local equation of the exceptional divisor is x prime equals 0, so I must factor out this factor. And so what remains is what we call the strict transform of the original curve, and it is non-singular. Just like on the picture, I started out with a singular curve, and I go to parabola after blowing up. Okay, so we'll need more general blowing ups, so let me define those. So we can blow up. let's say, an n-dimensional Euclidean space at the origin. So this is similar. I have a n-dimensional space. Again, I consider the totality of straight lines passing through the origin. Now, this time they're parameterized by Pn minus 1. Okay, so I remove so the center of blowing up is the origin, the exceptional divisor is Pn minus 1, and everything else remains unchanged. So I have a bunch of lines upstairs which no longer intersect each other. I don't know if it helps, maybe helps some people. This here is a total space of the line bundle on Pn minus 1 whose Chern class is minus 1. And if you collapse the zero section, you get the n-dimensional Euclidean space. And again, I have, similar to the previous case, I'm interested in having explicit equations for everything. So now upstairs is covered by I coordinate charts, and the coordinate chart number I looks like this. Okay, and so that's blowing up Euclidean space at the origin. We could blow up the Euclidean space along a linear subspace. Maybe I'll just go over this very quickly. So blowing up Kn at Euclidean subspace, say Kn minus L. So I'll just go over this very quickly. So here, the center of blowing up is the Euclidean subspace defined by, let's say, the first L variables vanishing. So I'll go this very quickly. Just think of taking a cross section of this by KL, by an L-dimensional space, and recreating this picture with n replaced by L, and then taking a direct product. There's this this kind of trivial Kn minus L along which nothing happens. So here the exceptional divisor will be a trivial bundle of PL minus 1s. And there is a similar, let me not write down the coordinates to save time, but it basically looks exactly like this, except we replace n by L, and then we have some trivial coordinates where nothing happens, namely xl plus 1, xl plus 2, and so on until xn. Okay, and finally, the most general blowing up that will appear in today's talk and Sunday's talk is the following. You can blow up along any ideal, along any subvariety, any subscheme. So let me just define this quickly. This is a generalization of what we have seen until now. Okay, so blowing up along an ideal. So let X be an affine variety embedded in some Kn, given by some equations. Say Fs equals 0. So Franz Victor mentioned the coordinate ring. The coordinate ring of this is so it's A modulo F1 Fs. And let's consider an ideal of A, generated by certain generators, say L. So what does it mean to blow up along this ideal? Well, it means we look at the X minus the zero locus of I, minus the subscheme or subvariety defined by I, and we consider the map to KL minus 1, where L is this number, which just sends okay, phi. And then we take the graph of phi inside X and take the closure, take the Zariski closure. So we have a projection of the first factor. This is obviously a birational projective. Oh, sorry. What did I say? Oh, what did I say? P minus 1. Yeah. P minus 1. Yeah, this is obviously, yeah, so this was a map from this variety to the projective space, well defined because I'm away from the zero locus of phi, so these don't vanish simultaneously. So now I can take the closure of the graph of phi. And consider the projection of the first factor. It's obviously a birational projective morph. It's projective because it's embedded into X cross projective space, and it's birational because it's a graph of something, of a mapping over an open set of X. So that mapping phi gives the inverse over that open set. Okay. And so the problem of resolution of singularity is just to prove that it exists or construct it. And yeah, I won't give the full history of the subject. I guess the curve case is attributed to Newton and Puiseux and Riemann by complex methods. And dimension 2 was done by was done by the Italian geometers in the early 20th century. Zariski later pointed out that none of their proofs are complete, and some were completely wrong. Jung, but they had the idea, they had the gist. Jung proved it in the early 20th century by using analytic methods, and then the first rigorous proofs were given by Walker in 1934 and Zariski in 1939. I'll dwell on Zariski's contribution. And dimension 3 was Zariski around 1940. Okay, and then I'll talk about Hironaka's work later. So in this talk I want to give an introduction to resolution of singularities by concentrating on valuations, valuation theoretic methods, which were introduced by Zariski, I guess building on some ideas of Krull. So now we start a new topic, valuation. So yes, I'll probably repeat. I don't know what Franz Victor said in the first day, so I'll probably repeat some things, but so remember that. So I'll start with a field, capital K. In my examples that interest me, it will be usually a field of rational functions of some algebraic variety, some singular algebraic variety. So consider evaluations are homomorphism, so let's say surjective homomorphisms from K star to some ordered group. It's called the value group. Such that, so it's homomorphism, such that the value of the sum is greater than or equal to the minimum of the value. So you should think of this, you can think of this as a generalization of order of vanishing of a rational function along a, say along an algebraic variety. Okay, and the reason I'm repeating this, that probably everybody knows, I want to stress one thing, that equality holds if nu of x is different from nu of y. This is this is a part of the definition. This is actually a consequence of the definition. It's very easy to prove this from here, but this will be crucial in what comes later. And so valuation rings also came up already. So associated to nu, we have a notion of a valuation ring. We have a local ring. So here the convention is, yeah, I'm a little sloppy. I didn't define, nu of 0 is not defined, but by convention is greater than anything in gamma, okay? So nu of 0 is plus infinity. Okay. The maximal ideal is consists of all elements. So the elements of non-negative values form a ring, and those of strictly positive values are the maximal ideal in this ring. And Franz Victor already mentioned there are various ways to characterize valuation rings. Franz Victor already mentioned one. Maybe he mentioned more on the first day, but I'll say this again because there's one particular characterization which I need for geometry. Okay, so we have the following theorem. So I start with the integral domain with field of fractions k. Okay, and then the following are equivalent. So first of all, R is a valuation ring for some valuation. For some valuation nu. The second, this is the one that Franz Victor mentioned, is for any element x in K, non-zero, either x in R or 1 over x is in R. Of course, it's an inclusive, or it could be both, right? The third is that ideals, the set of ideals of R are totally ordered by inclusion. And the most important one for the geometric interpretation is the following. I'll state it, then I'll need a definition to state it. Okay, so R is maximal among all the local sum rings of K, is maximal with respect to the relation of birational domination. So let me tell you what birational domination is. Okay, so let be two local domains. I guess well, it doesn't really matter for the definition, but I'm assuming they have the same field of fractions. I mean, I could define domination without birational, but so okay, yeah, let's say having let's say with field of fractions K. Fractions K. So R2 dominates R1. So it's written like this. If two conditions hold, first of all, R1 is contained in R2, and secondly, the maximal ideal of R2 is a contraction of the maximal ideal of R1 is a contraction of the maximal ideal of R2 to R1. Example. So example. So every time we blow something up, we have an example of birational domination. So example is just take some blowing up, let's say x prime goes to x, take a point on x, and take a point xi prime in the preimage of xi, okay? So I'm just assuming that p of xi prime equals xi. That's, in this situation, this is exactly what happens, right? First of all, the local ring that xi is contained in the local ring of xi prime, and the statement that this statement is exactly the statement this happens to the maximal ideals. Okay, the fact that xi is the image of xi prime is exactly the statement. Okay, so for example, more specific, let's take one of the examples that I had on the board. So for example, let's take the plane, let's take the origin of the plane. So this is a local ring, so all the rational functions where denominators don't vanish at the origin. And let's take a point upstairs, let's say the origin of one of the coordinate charts. And then it's very easy to check that this holds. Right? One ring is contained in the other, and the maximal ideal contracted here gives you the maximal ideal. Okay? Okay, this theorem is easy to prove. It's proved in many commutative algebra books. I think mostly, for example, in ITM McDonald, it mostly contains a. Maybe one small remark is when you prove 3 implies 1, in particular, you start with a ring with ideals that are you have to reconstruct evaluation. So in particular, the valuation ring determines the valuation uniquely. That's just a remark. Okay, so what's the relation with resolution of singularities? Okay, let's take my singular variety X. Let's consider the following. Let's consider that's Zariski's work from around 1940. Let's consider the totality of all the possible blowing ups along all possible ideas. Well, I forgot to say here when I defined blowing up is that I defined it for X affine, but of course, even if X is not affine, you can blow up along a sheaf of ideals. Those local blowing ups glue up naturally. So anyway, take X, whether affine or not, and consider the totality of all the possible blowing ups along all the possible ideals. So this is a huge collection of objects, but we can think of it as a projective system. Okay, so what that means is that given 2 blowing ups, you can always form a third, which dominates them both. That's what it is called. This is the graph of the birational correspondence between X alpha and X beta. It's not exactly the fiber product. It's a subset of the fiber product. Okay, it's, if you like, all these 3 varieties share a common Zariski open set, so which therefore embeds isomorphically into the fiber product, and X alpha beta is the closure of that common Zariski. It's an irreducible component of the fiber product. Okay, and so since we have a projective system, we can take the projective limit. So there's some kind of sky which sits over every single birational model. Okay. And the theorem of Zariski, which is not too hard to prove, is that oh, actually, yeah, maybe before I say that, there's one more definition I want to give, which is, I mean, in a sense, implicitly was already given by Franz Victor. And okay, I take evaluation of field K, and I take a point on the algebraic variety X, or yeah, maybe I should. Let me see. Okay, let me go here. So in general, if I have a local domain with fraction field K, and evaluation nu, then I say that nu is centered at R or at M if Rm is birationally dominated by R nu, M nu. Okay. This is just another way of saying, this is the same as saying that the valuation is non-negative on R and strictly positive on M. Okay, so I have the notion of the center of the valuation. And so if I have a point on an algebraic variety, I say that nu is centered at Xi. If the local ring at the point is dominated, I mean, if it's centered in the local ring, if the local ring is dominated by the valuation ring. Okay. So this is this actually this appeared almost exactly like this in Franz Victor's talk, in the sense that, so if I have the so Franz Victor was talking about a map, an injective homomorphism from the coordinate ring to the valuation ring, but the coordinate ring is contained in the local ring. And so what I'm saying here is really exactly the same as what Franz Victor was saying. Okay, so now I can state Zariski's theorem. It's around 1940, I think. He said that there is a natural bijection. There is a bijection between this S and the set of all valuations nu centered at points of X. Okay. Okay. This, by the way, Zariski called this the abstract Riemann surface of a field, which I think is a very bad name, but his motivation was that in case X has dimension 1, let's say we're over the complex numbers, then this projective system is very simple. It only contains finitely many elements, finitely many objects, and the limit is the resolution of singularities, which already dominates every other model. So it is the Riemann surface in that case. But starting with dimension 2, it's a huge object. It's not a variety, not a scheme. Okay, so the proof is easy. It's very natural. So you can just one can just define the maps in both directions. So okay, so if I start with evaluation, give it new, let C be its center on X, and then there is a something that maybe I should have mentioned earlier. This is called the valuative criterion of properness. Okay, so so in this situation, for every blowing up, there is a unique point. Every blowing up X alpha, there is a unique point C alpha where my valuation nu is centered. That's called the valuation criterion of properness. It's also not hard to prove by hand. So you see, if I start with starting with evaluation, I can give you, for every projective model, it determines a point on that projective model in a way which is compatible with the arrows. That's exactly an element in the projective limit, right? Okay, and conversely, given, okay, take an element in the projective limit, so I can consider local rings at each point, and so given, let's say x gamma to x alpha, c gamma and c alpha. So for every arrow in my projective system, I have the corresponding local rings, and I now have the maps, arrows that go the other way. And the arrows here, they're precisely birational dominations, right? So now I get a direct system of local rings where the morphisms are birational dominations. So it's not, and so I can take the direct limit, and it's not surprising that the direct limit turns out to be a maximal element with respect to birational domination. You need a short argument to prove it, but it's, anyway, at least it gives you an idea. And then Zariski introduced a topology on it, Zariski topology, which is just, by definition, the inverse limit topology. Limit topology. Of the Zariski topologies on all the X alphas. So it's the coarsest. So I take the Zariski topology on each X alpha, and I take the coarsest topology on S, which makes all the arrows continuous functions. So it's a topology generated by the preimages of all the Zariski open sets of all the X alphas. And there is a theorem due to Zariski and characteristic 0 and Chevalier in general, that S is compact, or quasi-compact, as the French people say, because it's not Hausdorff. It's not too hard to prove. Especially Chevalier's proof is very beautiful. I won't give it for lack of time. I just tell you the idea. So if we were dealing with Hausdorff spaces, this is a standard result in topology. Inverse limit of compact Hausdorff spaces is compact because it embeds as a closed subset into the direct product. The direct product is compact by Tikhonov's theorem. So this proof fails for non-Hausdorff spaces because the embedding into direct product is not a closed subset. And so Zariski's idea was pass to a finite topology, use the standard theorem, and then observe that if something is compact in the finite topology, it is also compact in the coarser topology. Right? And so what in Zariski's case, he was dealing with projective spaces over C. He switched to classical topology, used the standard theorem, and then said, well, then it's even more compact in the Zariski topology. And then Chevalier came up with a general proof in full generality where he used the same structure, the same plan, but I won't tell you his proof. It's not long. Okay. And so this is what, towards the end of Franz Victor's talk today, that's what he said, that valuation give you a way of separating the problem into local and global. Okay, so now I can make this rigorous. Local means with respect to some topology. So in this case, with respect to Zariski topology. Okay, so local uniformization problem. Construct. So fix evaluation nu. Fix evaluation nu. Construct a birational projective morphism such that the center, fix nu. So nu is centered at some point C of x, and as I said, in this situation, there is a unique center of nu on x prime. Okay, such that the center C prime of nu on x prime is non-singular. And as Franz Victor mentioned, Zariski was able to prove this in characteristic 0. This is also around 1940. So Zariski proved this in characteristic 0. In characteristic 0. And then his plan to continue was the following. So you see, so local uniformization theorem says that for any evaluation nu, any element of S, we can construct a local uniformization with respect to this nu. That means that, okay, so construct a local, let's say, x prime. The center of nu is nothing but the image of nu under the natural map from S to x prime. Okay, so, but the point is that being non-singular is an open condition. Regular locus is open. So if you construct a local uniformization with respect to a certain C, with respect to a certain nu, that means here there's a whole open set of points which are regular, okay? And therefore its pre-image here will give you an entire open set. So once you construct a local uniformization with respect to nu, you automatically construct one in an entire open set in the Zariski topology. And so that was Zariski's idea, that since we can do this for every single nu, we get an open covering of S for which we can select a finite subcovering. So what is the final upshot of all this? So the local uniformization theorem implies the following, that we have finitely many partial desingularizations. Yes. So let me call the natural maps, let's say rho 1 to rho r, such that such that if you take a regular locus, a non-singular locus, on each xi, look at its preimage at S, the union of these guys covers everything. And so it seems like now we're almost done, right? Because now we just have to, what remains is to prove the following patching theorem. It seems like now we're very, very close to globalization. So now I'm discussing how far is local uniformization from global resolution of singularities. As Franz Victor said, resolution of singularities obviously implies local uniformization, because if I can make every point non-singular, in particular the center of nu is non-singular, the converse it turns out to be much harder than people thought. So what remains is the following patching theorem. So we can go by induction on R, so it's enough to do 2 at a time. So let's say we have x1 and x2. So I want to construct x1, 2. So let me call this lambda 1, lambda 2. x1, 2, such that the regular locus of x1, 2 contains the union of regular locus of x1 and the regular locus of x2. Okay, so yeah, I guess my time is almost up. So let me just say very quickly that this turned out to be a hard problem, which Zariski solved in dimensions 2 and 3, and then Hironaka gave a global proof without going through valuation theory, without using any of these considerations. And so now valuation theory is coming back into fashion in this context, because I think in characteristic P, we don't even know local uniformization yet, so this is obviously the first thing to attack. And maybe just in the remaining 3 minutes, I'll say something I'm planning to say at the end anyway, which is kind of fast forward to the end. I didn't have time to explain Hironaka's proof, but there's a crucial step. So let's say we have a So let's say our singularity is defined by a Weierstrass polynomial of multiplicity mu. So here x is a multivariable. And let's assume that the multiplicity of each phi I at 0 is strictly greater than I. So the whole thing has multiplicity mu, and this is the only term of multiplicity mu. So the absolutely crucial step, the first step in Hironaka's proof is passing to the maximal contact coordinates, or Chernhausen transformation. So this is making the change of variables. Okay, so it's making this change of variables, which kills this term. And these maximal contact coordinates have very good properties. They're stable under coordinate changes. They're stable under blowing ups, as long as the blowing ups don't lower the multiplicity. So this is what allows Hironaka to set up his induction. And so I guess in the remaining minute, and this is exactly the step that goes wrong in characteristic P. Well, naively, you might say, well, if P divides mu, this expression makes no sense, right? But which is the difficult case. But maybe slightly more sophisticated explanation is this is absolutely not stable under any sort of coordinate changes. So I guess in characteristic P, a kind of known difficult case which contains all the phenomena, or all the difficulties of the problem, is this kind of equation. Actually, Michael Tiomkin proved, it's a theorem of Michael Tiomkin that to prove local uniformization in this case is enough to prove it in general. So now we know that this case is enough. In any case, the natural idea, the natural replacement for maximal contact here would be to absorb all the p powers from G into Y. But this is very bad in the sense that it's not stable under coordinate changes. So you see, for example, here there are no p powers in the G. But if I make a change of variables, let's say if I replace x1 by x1 plus x2, all of a sudden I get a p power, which I again have to absorb into Y. And so in the very last thing, my time is up. So the very last thing I'll say today. So let's consider the situation. In terms of valuation theory, a natural idea for maximal contact is to maximize the valuation of this coordinate, maximize the value. So one might try to do this here, and the difficult case is the following. So it may happen, so let's assume I have a fixed valuation. It may happen that, so let's consider the following set. Let's consider all the possible changes of variables, so to speak, possibly after blowing up y minus a rational function of x. Okay, and and it turns out it may happen that this set does not have a maximal element. And this situation, this condition, this is exactly equivalent to the statement that the field extension, the extension. So k of x1. Okay, let me use multivariable for x. So is defect. Okay, so this is a defect that Franz Victor was talking about, and this is a difficult case in characteristic P. Okay, so I'm really out of time now. Thank you.